How's it going, guys? My name is Ashton Kupka, and this is Midterm Checkpoint 1. So today we're discussing our 4 problems given to us. And number 1, we're going to start off with let S be the set of numbers 1, 2, and 10, and a set of each statement is true. So, statement 1, S is an element of the power set of all positive integers. Since we know that the power set of all positive integers is first going to contain the set of numbers that contain no elements, so the empty set, and then it's going to contain the set of numbers with only one element, so 1, -1, 2, 3, and so forth, all the way for all integers. Then it's going to contain the set of numbers with two elements, so 1, 2, 1, 3, 1, 4, and all the way down until all the elements have been taken. And then it's going to contain the set of numbers with three elements, so 1, 2, 3, 1, 2, 3, 4, and so forth. And then since it contains all of those of three element sets, then we know that S is actually going to be contained in the power set of Z. However, so the first statement is true. However, if we look at the second statement, which S is a subset of the power set of Z, since the power set of Z we know only contains set of numbers, and for a set to be a subset, every element has to be contained in that set, then we know that the power set of Z contains no elements containing of 1, 2, or 10. It only contains the set of numbers. So therefore, S is not a subset of the power set. Moving on to number 2, we can configure two open incentives of P of x and Q of x with a property that for every x in the set of all integers, P of x implies Q of x is false, but for there exists an x in the set of positive integers such that P of x implies Q of x is true. So, to disprove the first statement or make sure that it's false, we can just use a counterexample. So let, for example, P of x be the absolute value of x is less than 3, and that Q of x is x plus 1 is greater than 2. And then we look at, from a counterexample perspective, to disprove for every x, we just look at x equals -2. So P of x of -2 is going to be the absolute value of 2, which is less than 3, so that's true. And then Q of x of -2 is going to be -2 plus 1, which is -1, which is not greater than 2. So this is false. And since Q of x is false and P of x is true, there is no implication. And the only case that we get the implication is when P of x is true, Q of x is true, or when Q of x is true, and P of x can be any value, and finally when they're both false. So P of x is false and Q of x is false. Now, for looking up an example that there exists an x in Z such that P of x implies Q of x, we can consider 2. So P of 2 is going to be the absolute value of 2, which is less than 3. This is true. There we go. And then Q of x of 2 is going to be 2 plus 1, which is 3, which is therefore greater than 2, so it's true, and since they're both true, the implication is true. Next, we can look at number 3. Consider a statement for every n in the set of integers. If n 0 mod 10, then 5 divides n. So we're going to go through each proof method we've discussed so far in class, so direct, contrapositive, and contradiction, and then show you the introduction and the final step / conclusion of the proof. So, for the first one, a direct proof, we're going to assume our P of x. So, suppose the statement n 0 mod 10 is true, it shows that n 0 mod 10 is equivalent to 10 divided 0 minus n, which is equivalent to 5 times 2 divide 0 minus n. Show a lot of math how it's true, and our conclusion would be, since our P of x is true for every n in n, it shows that from our work that 5 divides n. Next, we're going to look at the contrapositive. So we're going to assume that our Q of x is false. So assume that 5 does not divide n for every n in the set of natural numbers. Then do a lot of math to show why it's true. Conclusion, since 5 does not divide n, it shows that 10 does not divide 0 minus n. And then there's our proof. And then finally, contradiction. So we're going to assume on the contrary that P of x is true, but Q of x is false. So assume on the contrary that 10 divides 0 minus n, and that 5 does not divide n. We're going to do a lot of math, And then finally, we're going to reach an impossible statement. So our conclusion is going to be, this is impossible since if 5 does not divide n and 10 divides 0 minus n, we have reached a contradiction. Therefore, our assumption is false that 5 does not divide n. And our final problem today is going to be, make the statements about Cartesian products of sets that can be proved with an example and other cannot be proved, and explain whether they're correct. So, for example, that cannot be proved, but is a true statement, is let A and B, with an example I should say, let A and B be sets and assume that small a is an element of A and small b is an element of B, then there exists an alpha in the cross product of A cross B such that alpha equals AB. So we don't need an example here because everything is already given to us and the statement is therefore already necessarily true. So there's no example we need to further explain why this is true. We'd have to go about showing that it is true and writing that it's true. And then our final one that does need example would be let A, B, and C be non-empty sets. And then we need to prove that A cross B is a subset or equal to B cross C if and only if A is a subset or equivalent to the set of B. And then this will require us to insert variables into them, saying A, let's consider A being an element of A, or C being an element of C, and then so forth. And we have to prove it from there. So that concludes everything, and I hope you guys learned something. Have a good one.